Excellent. Linear algebra, lecture 3. So we've been talking about one linear equation in n variables. So it's an equation that looks like a1x1 plus a2x2, a3x3 up to an xn equals b. The equation is homogeneous if b is equal to 0, inhomogeneous if b is not 0. So one linear equation is pretty simple, but even from just looking at one linear equation, we were led to the concept of vector spaces, subspaces, and affine subspaces. So let me review all that quickly. So let's call this equation star. We write equations, the solutions of equation is written as a column vector. x1, x2 down to x sub n. And the set of all column vectors is what is called Rn. This is our prototypical example of an n-dimensional vector space. But we'll see what those words mean soon enough. So the solution space of equation star is the set of all vectors x equal x1, x2 down to x sub n in Rn that solve the equation. That's the solution space. And again, this is all a quick review. Let's consider first the homogeneous case. Suppose you have the homogeneous equation, a1x1 up to an xn equals 0. Let W be the solution space. That means all vectors that satisfy this equation. So if x, which is this column vector x1 up to xn, is in W in the solution space, and if the vector y is in W, what does that mean? It means that a1x1 plus a2x2 up to an xn is 0. And a1y1 plus a2y2 up to an yn is 0. We have both of these equations are satisfied. So if you add the equations, you get a1 x1 plus y1 plus a2 x2 plus y2 and so forth up to an xn plus yn equals 0 plus 0, which is 0. Which means if I take the vector x plus y, so the sum of two vectors is the vector you get by adding their coordinates, x1 plus y1, x2 plus y2, down to xn plus yn. This is also a solution. So if you look at the solution space of a homogeneous equation, because 0 plus 0 equals 0, this is the crux of the matter, the sum of two solutions gives another solution. Also, if you take this equation and you multiply it by c, C times A1 x1. So C is just a scalar. That means a real number. C times A1 x1 plus C2 plus A2 x2 up to AN xn is C times 0, and C times 0 is 0. If I distribute this across, C A1 x1 is the same as A1 C x1. C A2 x2 is A2 C x2. And so forth, AN CXN equals 0. So I have a new solution of the equation with coordinates CX1 down to CXN, which is exactly what we define to be the scalar multiplication of the vector x by c. So if x is in the solution space W, CX is also in W. Okay. If you have is there a question about this?
Yes, I have a question.
Go ahead.
So I see above where you put the homogeneous that equals to 0. Automatically, you knew it was A just because that's the formula.
I'm sorry, automatically I knew what?
Automatically, you knew that it was A1 x1 because that's the formula of homogeneous.
No. So this is what every linear equation looks like this. Every linear equation. Of course, you can use different letters for the variables, you can use different letters for the coefficients, but this is a linear equation in n variables. And the right-hand side is a number, a scalar b. If this number is 0, the equation is called homogeneous. If this number is not 0, the equation is called inhomogeneous. But this is the general form of one linear equation.
Okay, and the last problem that you did, can you explain it one more time?
Well, it wasn't a problem. I'm looking at the set of all solutions of my equation. Right? So this is my equation. Looking at the set of all solutions, that's what's called the solution space. I'm calling it W. So W is all vectors that solve this equation. So if X is in W, that means if this vector is a solution of the equation, that means that this relationship is true. If I take this relation and I multiply it by C, I get C times the left-hand side of the equation equals C times 0, which is 0. But if I distribute this number C across, I can write the equation like this. And now I have a vector that's a solution of the equation where the coordinates are CX1, CX2 up to CXN. So if I take the scalar multiple, I take the vector X, I perform scalar multiplication by C, I get a new solution. So my solution, what I just proved, is that the solution space of a homogeneous equation is closed under vector addition and under scalar multiplication.
So where it says C times 0, why is it 0?
Any number times 0 is 0.
Okay, but how did you distinguish that from C and then inside the parentheses?
Well, no, nothing's being distinguished. Here I have this equation, right? X1 up to Xn is a solution of this equation. This is a number. That number is equal to 0. Multiply by a number C, I get this. Multiply 0 by C, I get 0. Right? If something is 0 and you multiply it by C, you still have 0.
Okay, you got 0 just because it equals to 0, which says on the top.
Correct.
Okay.
Question.
Yeah.
In the addition proof, how did you conclude that when you add X and Y, that's also a subset, I mean, a member of W? How did you jump from?
So I have this equation, okay? All right.
Right.
I have this equation. Okay,
Yeah.
I add them.
Yeah. Yeah, but then how did you jump from that step after you added it to saying that?
So when I
Therefore-
add it, I get this.
Right.
A1 times the number x1 plus y1 plus A2 times the number x2 plus y2 and so forth gives me 0.
Ah, okay.
That says that the vector with these coordinates, x1 plus y1, x2 plus y2 and so forth, is in the solution space.
Okay, yeah, got it. Thank you.
Okay. So a set W contained in Rn, this means a subset Rn. Rn is all vectors, and W is a subset of Rn, is called a subspace, or it's also called a vector subspace. If the following three conditions are satisfied, first, the zero vector is in W. Second, if whenever x and y are in W, then x plus y is in W. So this means that W is closed under vector addition. That's what this says. If you take two vectors in W and you add them, you get another vector in W. And third, if x is a vector in W and c is any scalar, that means a number, then c times x is in W. So W is also closed under scalar multiplication. So that's what a subspace is. A subspace is a subspace of a vector space that contains the zero vector and is closed under vector addition and scalar multiplication. So what we just proved is that the solution space of a homogeneous linear equation is a subspace of Rn.
I have a question.
Yeah,
So I understand the subspace of a vector, but can you explain number one?
this?
Yeah.
Well, the zero vector in Rn is just the vector, all of whose coordinates are 0. This is the zero vector. It's not the number 0, it's the zero vector. It's like if you took, if you look at vectors in the plane, every vector has a pair of coordinates and the origin is 0, 0. That's the zero vector in R2, right? And if I have the equation a1 x1 plus a2 x2 up to an xn equals 0, a homogeneous equation, if I let all the x's be 0, a1 times 0, a2 times 0, an times 0, this is just 0 plus 0 plus 0, that's equal to 0. So the zero vector is a solution of every homogeneous equation. But this is the zero vector.
Okay.
So a subspace has to contain the zero vector.
And the W is on the right side because that's just saying the spaces of the vector.
Well, I'm not, I mean, W is on the right side of what?
Number one.
So you have to know, or if you don't know, you have to learn, and I think it's an appendix, just the language of set theory. W is a set. This means 0 is an element of this set. So this is a set of vectors, and this set of vectors contains the zero vector. That's what this says.
Okay. And number two, basically that's with the same thing, which is x1, y1, then it's just a pair of a set.
This says if X is a vector in W, and if Y is a vector in W, and you add the two vectors, you get another vector in W.
Okay.
Right?
Thank you.
This is not always the case, but if you have a subspace, it is always the case.
And in number three, how did you get CX at the end?
It's not how I got it. This is a part of the definition. You're allowed, if you have a vector and a scalar, you can multiply the vector by a scalar. And this is the definition. This is a definition. So I'm not proving anything. I'm just defining what is a subspace. A subspace is a set of vectors in Rn that contains zero, is closed under vector addition, and is closed under scalar multiplication. That's just a definition of what is a subspace. So,
Okay.
right. Let's look at a inhomogeneous equation. Suppose I have, so this is the inhomogeneous case. A1x1 plus A2x2 up to an xn equals some number b, which is not zero. And suppose I let L be the solution space of this equation. So this is some subset of Rn. It's all vectors in Rn that are solutions of this equation. And if B, the right-hand side, is not zero, then the zero vector is not in L. So this symbol means not in the set L. Because if you make it all the x's equal to zero, the left-hand side is zero, so that can't equal the right-hand side, which is not zero. So if B is different from zero, the solution space of the inhomogeneous equation does not contain zero. So it's not a subspace. Couldn't possibly be a subspace. On the other hand, it turns out it's very close to a subspace, and that's what I want to explain now. So suppose that let W be the solution space of the homogeneous equation. Exactly the same equation, but with the right-hand side equal to zero. Oops. Make sure I'm using the same notation that I did in the notes. Okay. So suppose that V is a vector with coordinates v1, v2, down to vn, is a solution of the inhomogeneous equation. And X with coordinates x1 to xn is the solution of the homogeneous equation. So again, what I'm doing is really just high school algebra, but with a little bit more notation, perhaps. So I have A1 V1 plus A2 V2 up to AN VN equals B, because the vector V is a solution of the inhomogeneous equation. And I have a solution of the homogeneous equation, A1x1 plus A2x2 plus AN equals 0. So I have V is in L, the solution space of the inhomogeneous equation, and X is in W, which is the solution space of the homogeneous equation. And now I add these two equations. I get A1 V1 plus X1 plus A2 V2 plus X2 plus AN Vn plus Xn is B plus 0, which is still B. So if I look at the vector with these coordinates, that's a solution of the inhomogeneous equation. That is, the vector V plus X, which has coordinates V1 plus X1, V2 plus X2, down to Vn plus Xn, this is in L. So if V is in L and X is in W, V plus X is in L. Right. So V in L, X in W implies V plus X is in L. That's a very important relation. Another way of saying that is, if I take any vector in L, well, I'll just leave it like that. Or V plus W is contained in L. If I add to V any vector X, that's a solution of the homogeneous equation, I get a solution of the inhomogeneous equation. Okay, now, suppose I take two solutions of the inhomogeneous equation. So suppose that V prime, let's say it has coordinates V1 prime, V2 prime, down to V sub n prime, is also in L. So this means I have A1 V1 prime plus A2 V2 prime up to AN VN prime is equal to B. And I already had that V is a solution of the inhomogeneous equation. So A1 V1 plus A2 V2 plus AN VN is equal to B. And now I take these two equations and I subtract one from the other. If I subtract, I get A1 V1 prime minus V1 plus A2 V2 prime minus V2 and so forth, up to AN Vn prime minus Vn. I'm subtracting, I get B minus B, which is equal to 0. Which means if I look at the vector V prime minus V with coordinates V1 prime minus V1, V2 prime minus V2, down to Vn prime minus Vn, this is in W. So V prime minus V is some vector X in W. Or if I take this equation and rewrite it, V prime is V plus X for some X in W. So every vector, this says that every solution V prime in L, that's the solution of the inhomogeneous equation, is of the form V plus X for some X in W. So this says really that L is equal to V plus W. So this is very important. So let me explain again what this means. W is the solution space of the homogeneous equation. L, the solution space of the inhomogeneous equation. And V is a particular solution, just some solution of the inhomogeneous equation. So every solution of the inhomogeneous equation is a particular solution, but a solution of the homogeneous equation. So let me try and write down an example and see if I can solve it, and maybe see if we can figure out what all this means. Suppose I take the equation 2x plus 3y equals 17. So I could write this as 2x1 plus 3x2 equals 17. But I'm just going to use x and y as my variables instead of x1 and x2. Again, it's completely up to us what variables to use. So what is a particular solution of this equation? All right. So someone give me a solution of this equation. What's the vector that solves this equation?
We can do 3y equals 2x minus 17.
No, give me numbers x and y. I want
We could do-
the solution.
We could do 1, 5.
1, 5.
Okay, so if I take v equal to 1, 5, why is that a solution? Because 2 times 1 plus 3 times 5 is 2 plus 15 is 17. So this is a particular solution. Okay? What about for the homogeneous equation? So this is one solution. Not every solution, it's just one solution. In fact, give me another solution. That's another solution of this equation.
4, 3.
4, 3? Let's see. So 2 times 4 plus 3 times 3 is 8 plus 9 is 17. Excellent. So another solution, V prime, would be 4, 3. This is also an L. Okay, fine. So these are two solutions in L. So this is the inhomogeneous. The homogeneous equation is 2x plus 3y equals 0. What are the solutions of this equation?
-3, 2.
Well, that's one solution. Good. How do I find all solutions? So if W is the subspace of all solutions of this equation, well, I mean, you can do it in lots of ways. For example, if 2x plus 3y equals 0, then 3y has to equal minus 2x. So y has to equal minus 2/3 x. So if I take any value for x, y is minus 2/3 of x. Or this is x times 1 minus 2/3. So every solution of this equation is some scalar multiple of this vector, 1 minus 2/3. Or if I like, I could write this as, because I can write 1 as 3 over 3. And if I factor out the 3, this is like some x over 3 times the vector 3 minus 2. And if x can be anything, then really w, I can write w as the set of all scalar multiples of the vector 3 minus 2. So if I'm just looking at this very simple equation, 2x plus 3y equals 0, every solution of the homogeneous equation is some multiple of the vector 3 minus 2. I can write the solution space in other ways as well. There's nothing unique about this form of the solution, but every solution of this equation is some scalar multiple of 3 minus 2. Right? And I claim that L is equal to this vector 1, 5, a particular solution, plus W. That is, so that's what our theorem says. Every solution of the inhomogeneous equation is the vector 1, 5 plus some multiple of the vector 3 minus 2 for any number x. Or if I write this as one vector, this is 1 plus 3x, 5 minus 2x. So every solution of the inhomogeneous equation is of this form for some vector r. So this is the solution space for the inhomogeneous equation. It's all vectors of this form. If I let x equal 0, I recover the vector 1, 5. If I let x equal 1, I recover the solution 4, 3. But for any x, doesn't matter what x I pick, for any x, this is the set of solutions of the equation 2x plus 3y equals 17. So the solutions of this equation are the set of all vectors that look like this. All right. So this is the form in which we're going to write solutions of equations. So on the homework or on an exam, if you're given a question, write the solution space of the inhomogeneous equation 2x plus 3y equals 17. You can write it as this, where this is w, or you can write it like this, or you can write it like this. But this is the form in which the solution has to be presented. Right?
What's the L and the W? What's the difference?
W is being used for the solution space of the homogeneous equation. For W, we're looking at the equation 2x plus 3y equals 0. In L, we're looking at the equation 2x plus 3y equals 17. So W is the vector subspace of solutions of the homogeneous equation. L is the solution space of the inhomogeneous equation. Okay. And let me just add one final piece of terminology that's very important. If V is a vector and W is a set of vectors in Rn, then by the translate, or if we like, we translate W by the vector V, it's the set V plus W, which means it's the set of all vectors of the form V plus X, where X is in W. That's what we mean by a translate. And what is called an affine subspace is a set of the form V plus W, where V is a vector and W contained in Rn is not just a subset, but it's a subspace. So we just proved the following theorem. The solution space of an inhomogeneous equation is an affine subspace of Rn. The solution space of a homogeneous equation is a vector subspace of Rn. Of an inhomogeneous equation, the solution space is an affine subspace of Rn. That is a translate of a subspace. All right, so let's do another example. Let me pick one. Probably from the homework. So I'll give you a few minutes to do this right now. Compute the subspace of solutions of the homogeneous equation 5x minus 8y equals 0. So that's a vector subspace. And compute the affine subspace of solutions of the inhomogeneous equation 5x minus 8y equals 1. So let me pause the recording for a couple of minutes, and I want you, with pencil and paper where you are, to solve these two equations, and then I'll do it. Let's see. Any success? What do solutions of the equation 5x minus 8y look like? So if we have the equation 5x minus 8y equals 0, that's the same as 8y equals 5x. So y is always going to be 5/8 of x. So if xy is in W, the solution space of the homogeneous equation, then xy has to be x and y has to be 5/8 of x, which I can write as x times the vector 1 5/8. Or I could write this as x over 8 times the vector 8 5. If I do scalar multiplication, this is what I get. So every vector in W is some scalar multiple of x of 8 5. So I can write W as the set of all scalar multiples of the vector 8 5 for any x in R. So this is a subspace of R2. That's what W looks like. That's the solution space of the homogeneous equation.
I have a question.
Yeah,
At the end, why is it able to be x over 8 and then 8, 5?
so this means x over 8 for any number x. But every number you can write, like, every number can be written in the form x over 8. Like 3 is 24 over 8, right? Or 1 is 8 over 8. So if I'm looking at all possible values of x, all possible values of x over 8 for any value of x is the same as all values of x. It's just a simplification. If you wanted to leave it like this, it would also be okay. It's also true that W is the set of all scalar multiples of the vector 1 times over 5/8 x in R. These are exactly the same two sets.
Oh, okay.
But that's the solution space of the homogeneous equation. But now I want to find the solution space of this inhomogeneous equation. So I want to solve 8x, 5x minus 8y equals 1. So I just need to find one solution, and any way I can find one solution is good enough. So I could make, I don't know, I could just like try and guess a solution. Like if I take x equal 5 and y equals 3, 5 times 5 minus 8, 5 times 5 minus 8 times 3 is 25 minus 24 is 1. So the vector 5, 3 is in L, which is the solution space of the inhomogeneous equation. So just by trial and error, I found a solution. Or if I couldn't find one by trial and error, I could say, well, if I solve this equation for y, 8y is 5x minus 1. So y is any number of the form 5/8 x minus 1/8 minus. So if I took, for example, x equal 8 in this equation, I would get y is equal to, well, actually, if I just took x equal 1, for example, I would get y is equal to 5/8 minus 1/8 or a half. So 1 and a half over a half would be a solution. That would be a solution. I mean, there are lots of solutions. So 1 and a half is in L. So these are just two particular solutions of the inhomogeneous equation. But the general solution is L is equal to one particular solution, like 5, 3 plus W. So that's 5, 3 plus, what was W? W was the set of vectors x times 8, 5 for any x in R. So this is equal to the set of all vectors 5, 3 plus 8x, 5x for x in R. Or I can write this as 5 plus 8x, 3 plus 5x for any x in R. So every solution should be written, you should be able to write every solution in this form. For example, if I take in this x equals 0, I get 5 plus 0, 3 plus 0, or 5, 3. So that recovers 5, 3. What about 1/2? Suppose I take x equal to minus a half. If I take x equal to minus a half, 5 plus 8x, 3 plus 5x is equal to 5 minus 8 halves, 3 minus 5 halves. This is 5 minus 4, that's 1. 3 minus 2.5 is a half. And I recovered the solution 1.5. So the affine subspace of solutions of the inhomogeneous equation is this.
I have a question.
Yes,
Where it says L equals 5 to 3, did you choose 5 to 3 or?
no. Well, I was looking for a particular solution of this equation.
Okay,
And if I let x equal 5 and y equal 3, I get 5 times 5, which is 25, minus 8 times 3, which is 24, and 25 minus 24 equals 1. So that's a solution. So the vector 5, 3 is a solution.
okay,
And I just found that by sort of guessing and trial and error.
no problem.
So it could be any vector from L that could be V in the final solution, right? It doesn't have
Correct.
to be.
Like I could have chosen 1.5.
Oh,
So
okay.
if I had chosen, I could have said L is also equal to the vector 1.5 plus W. So that's the set of all vectors of the form 1.5 plus x times 8/5 for x in R, which I could write as 1 plus 8x a half plus 5x, that vector, for any x in R. And if I let x equal 0, I get the vector 1.5, of course. If I want to see if I can recover the vector 5/3, this was like x equal to a half, then this gives me the vector 1 plus 8 times a half, 1/2 plus 5 times a half. This is 1 plus 4, a half plus 5/2. That gives me back the vector 5, 3. But I could also write the solution space in this form. There's nothing unique about how the solution space is unique, but how you represent it, it can be represented in many different ways.
I have a question.
Yeah,
For the homework, it says to write the solutions of the linear equations as vectors. Do we have to write them in the subspace notation, or do we just leave them as vectors?
well, I think in the homework for today, I hadn't talked about subspaces yet. I was just talking about writing the solutions as vectors. So you can just leave it as vectors. In next week's homework,
Okay,
we
thank
talk
you.
about subspaces and affine subspaces. And then you have to use this better notation. Okay. Other questions? Okay, well, this is a discussion of one vector, one linear equation. But you know, in high school, you often had to solve two equations and two unknowns, like 3x plus 2y equals 18, and 4x plus 3y equals minus 5. So now we have, this is a system of two equations in two variables. And we want to solve that. Or sometimes there's no solution. Show there's no solution. I mean, if you had an equation like x plus y equals 0 and x plus y equals 1, this is another system of two equations and two variables, but this has no solution, right? Because you can't have x plus y equal to 0 and 1 at the same time. There's no solution because 0 is not equal to 1. So a system of equations does not necessarily have a solution. right? So when you're given a problem to find all solutions of a system of equations, one possible answer is the empty set. There is no solution. That's just the way it is. Okay. So now we're going to consider systems of equations. So a system of, let's say, m linear equations in n variables looks like this. You might have a11 x1, a12 x2, a13 x3, up to a1n xn equals b1. That's the first equation. And we write the second equation as a21 x1, a22 x2, a23 x3, up to a2n xn equals b2. All the way down to like the mth equation, am1 x1 plus am2 x2 plus am3 x3 plus amn xn equals b sub m. In general, the ith equation would look like ai1 x1, ai2 x2, up to ain xn equals b sub I. This is the ith equation. So this is a system of m linear equations and n variables. And it's homogeneous if all of the right-hand sides are zero, b1, b2, b3, b sub m equals 0. And inhomogeneous otherwise. So if a lot of these are 0, but at least one of them is non-zero, then this is an inhomogeneous system. The system's homogeneous only if every one of the equations has right-hand side equal to 0. And the system is non-zero if one of the coefficients of one of the variables, aij, is different from 0 for some ij. That is, if every coefficient of every equation is 0, that's the 0 system. That's pretty uninteresting. But if at least one coefficient of one variable is non-zero, it's a non-zero system. Okay. And everything we said about vector subspaces and affine subspaces for a single linear equation carries over to the case of a system of equations. So the solution space W of a system of homogeneous linear equations is a vector subspace of Rn. The solution space L of a consistent, I'll say what that means in a moment, system of inhomogeneous linear equations is an affine subspace of Rn of the form L equals V plus W, where V is in L, it's a particular solution of the inhomogeneous system, and W is the solution space of the associated homogeneous system. And we say that a system of equations is consistent if it has at least one solution. So, and the proofs are exactly analogous to the proofs in the case of just a single equation. If you have two solutions of the homogeneous equation and you add them, you get another solution of the homogeneous equation. And if you have a solution of the homogeneous equation and you multiply it by of a homogeneous system and you multiply it by a scalar, you get another solution of the homogeneous system. The question is, how to solve a system. And the classical technique is to use something called Gaussian elimination. So the answer is Gaussian elimination. So the idea is, if you have a system of equations, to do something to get another system of equations, which has exactly the same solutions, but is easier to solve. So two systems are called equivalent. So these are two systems of linear equations in n variables are equivalent if they have exactly the same solution spaces. Exactly the same solutions. And there's simple things you can do to a system of equations to get a system which is equivalent. So what shall I call this? So here are some operations on a system of equations you can do to get an equivalent system of equations. So you can interchange two equations. So, I mean, for example, you have the system 3x plus 2y equals 5, 7x minus y equals 11. That's a system of equations. Suppose I interchange the equations. 7x minus y equals 11, 3x plus 2y equals 5. So you might say, well, you didn't do anything. Well, I did something. I just interchanged two equations. The equation that was second is now first. The equation that's first is now second. But any solution of the first system is clearly a solution of the second, and conversely. So if you interchange two equations, you don't change the solutions. I can multiply one equation by a non-zero scalar. So for example, if I take this system of equations and I multiply the first equation by 9, I would get a new system. 27x plus 18y equals 45 and I'm not changing the second equation, 7x minus y equals 11. So I got from here to here by multiplying this first equation by 9, but it should be clear. If x and y solve the first equation, they solve this, and if x and y solves this, it solves this, because you're just multiplying by 9. So, right. So multiplying an equation by a non-zero scalar gives you a different but equivalent system of equations. And third, which is the most important one, I can add a multiple of one equation to another. So in this system, I take the first equation, I just write it, I don't do anything to it. But suppose I add 2 times the first equation to the second. So if I take this equation, 2 times this equation is 6x plus 4y equals 10. I multiplied this equation by 2, and I add it to the second equation, 7x minus y equals 11. And what I get is 13x plus 3y equals 21. So from this system of equations, I got a new system by adding a multiple of one equation to another. So I added 2 times the first equation to the second, I got this. Any solution of this system will be a solution of this system. Any solution of this system will also be a solution of this. So I have 3 operations that take a system of equations to an equivalent system. And the idea is, yes, is
I
there
have
a
a question. Yes, how did you get 13x?
6 plus 7,
Oh, okay, got it. All right.
and 4 minus 1 is 3, and 10 plus 11 is 21.
Okay, thank you.
Okay. Now, the idea of Gaussian elimination is to use these operations in a clever way to really eliminate variables. So you get a simpler system. So here's a system of 3 equations in 2 variables, right? The number of equations, the number of variables can each be anything. You don't have to have 2 equations and 2 variables. You can have 15 equations and 100 variables, or 100 equations and 15 variables. But here's an example. Let's take 4x plus 11y equals 115. X plus 7y equals 67. And 8x minus 5y equals minus 13. So I have 3 equations in 2 variables, x and y. And I want to find all solutions. So I want to compute L, the solution space of this inhomogeneous system. So the first thing I'm going to do, I happen to like the simplest equation in x is the second. So I'm going to interchange the first and the second equations. What I'm doing, you don't have to do. You can solve these equations in lots of different ways. This is just one way to approach it. So all I did was I interchanged equations 1 and 2, right? The second equation is now the first equation is now the second, and the third is left alone. Okay. Now what I'm going to do is I'm not going to touch the first equation. I'm not going to touch the third equation. But I'm going to add minus 4 times equation 1 to equation 2. Or the same thing as saying, I'm subtracting 4 times the first equation from the second. So 4x minus 4x is 0 times x. 11 minus 28x is 11y minus 28y is minus 17y. See, actually, let me just write this out exactly. So I have, this is my second equation, 4x plus 11y equals 115. Multiply the first equation by 4. I get 4x plus 28y. If I multiply this by 4, 4 sevens are 28, 4 sixes are 24, 26. If I subtract, I get minus 17y. So it's this minus this equals minus 153. Minus 153y. Okay. Let's see, let me keep the first equation the way it is. And the third equation the way it is. If I multiply the second equation by minus 1 over 17, or if I divide by minus 17, I actually get y equals 9, right? Divide by minus 17, y equals 9. Actually, that's pretty good. If y equals 9, let's see. Suppose I add 5 times this equation or I can actually solve the equations now. If y is equal to 9, that means x plus 7y equals 67. So x is 67 minus 7y. That's 67 minus 7 times 9, which is 67 minus 63 is 4. Let's see if that's consistent. And this equation says 8x equals 5y minus 13 is 5 times 9 minus 13 is 45 minus 13 is 32. So x equals 4. So without doing very much work, I found this system of equations, actually it has a unique solution. xy equals 4, 9. So this system of equations has exactly one solution, 4, 9. You plug in x equals 4, y equals 9. It works. Yeah. That's interesting.
Professor, I have a question.
Yeah.
Is this sort of so using the second step there, which I think is the third step previously, that's just based on intuition? You kind of guess and check? Like how did you decide to take that step? Meaning to get the minus 17y equals minus 163y.
Okay. So so if you do this a lot, you try one thing and then another thing, and eventually you develop some skill or some intuition about what might work quickly. However, you don't have to rely on skill and intuition. And there's actually a strategy which always works, which I will describe right now. Okay? So, I mean, some of it, I mean, a lot of this is basically what you learned in high school. Like, I mean, I'll make up two equations, like 7x plus 2y equals 11, 4x minus 3y equals 19. So there's two equations and two unknowns, and you want to try to solve them. So what could you do? Well, things are always easier if you have like an x with a coefficient of 1. So suppose I multiply this first equation by 1/7. I get x plus 2/7 y equals 11/7, and 4x minus 3y equals 19. So I just multiplied this equation by a seventh. So this is a coefficient of 1. Now, if I take this first equation, I'm not changing it, but I take this equation minus 4 times the first equation, I'm eliminating an x. So 4x, so I have the equation 4x minus 3y equals 19. Take this equation and multiply it by 4. I get 4x plus 8/7 y equals 44/7. When I subtract this minus this, the x's cancel. I get minus 3 minus 8/7y equals 14 equals 19 minus 44/7. So, you know, I have to deal with fractions. This is 24, this is 21/7. So this is minus 29/7y. Let's see, what's 7 times 19? 19 times 7 is 133. 133 minus 44 is 89, is minus 89/7. So this equation becomes minus 29/7y equals minus 89/7. So, or I could multiply by 7 over minus 7/29. I get x plus 2/7 y equals 11/7. And this says that y is equal to 89/29. So I found y, and so x is minus 2/7 y plus 11/7. So I plug in y and I find x, right? I mean, that's
I have a question.
yeah.
On the right-hand side, where you got negative, I believe 24, and the denominator 7y equals 89, and then 7. Can you explain that on the right-hand side?
Over here?
Yes, the fourth row.
So let me,
Negative
so I
29.
started with these two equations.
Okay.
And my first step, again, I'm not saying this is the best way to solve it. It's certainly not the only way. This is just a way that works. I just want to find the solution. So you don't get you only get points if you solve the problem, not if you don't solve the problem. So, and how you solve the problem is generally up to you. So take this equation and divide it by 7. So I get x plus 2/7y equals 11/7. So that was my first step. Then I want to eliminate 4x from the second equation. So I'm going to multiply the first equation by 4 and subtract it from the second equation. So the second equation is 4x minus 3y equals 19. If I multiply this equation by 4, I get 4x plus 8/7y equals 44/7. So when I subtract the second equation minus, so I'm adding minus 4 times the first equation to the second. That means I'm subtracting 4 times this from this. The x's cancel.
How did you get 44/7?
I'm multiplying this equation by 4.
Oh, okay.
So 4 times 11 is 44. 4
Okay.
times 11 over 7 is 44 over 7. I'm multiplying this equation by 4 to get that. Because then when I subtract, the x's get canceled. I eliminate the x. I just get minus 3 minus 8 over 7 times y is 19 minus 44 over 7. And then I just do arithmetic. 21, this is minus 29 over 7 times y is, let's see, 7 times 19 is 133. 133 minus 44 is 89. So I get sorry, it should be a plus, I think. 133 minus is plus 89 over 7. So this equation is minus 29 over 7y equals 89 over 7. If I multiply, yeah, go ahead.
How is it 89 over 7?
19 minus 44 over 7 is 133 over 7 minus 44 over 7. Oops. Right? Is 89 over 7.
So I see that's 133. Where did you get 133?
So when I subtract, I'm taking this equation minus this equation. On the right-hand side, I get 19 minus 44 over 7. Right? This minus this. I'm subtracting, I have this equation minus this equation. So I have 19 minus 44 over 7, which is 89 over 7.
Yeah, because I see you wrote 133. So that's where I got confused of
Well,
where
19 is equal to 133 over 7. I'm subtracting, so I have to put fractions over a common denominator. Common denominator would be 7. So 19 is 133 over 7. And when I subtract, 133 over 7 minus 44 over 7 is 89 over 7.
Okay, and what could help me to to know, because I know you knew that automatically 19 is 133 over 7. How can I learn to know that the way you did?
Well,
I
you
think
wanna
he
write-
multiplied
yeah, you
I'm sorry.
multiply 19 by 7.
by 7 to get the common denominator is 7.
Yeah, I mean, 19
Okay, 19
times
times
7
7.
is
It's
133.
Okay, now I understand.
Right? But I mean, if you're not used to doing arithmetic, then in linear algebra, you'll get used to doing arithmetic. You have to solve you have to solve the problems.
Okay.
Right? Okay. So this is 89 over 7. So if I multiply by minus 7 over 29, I get minus 89 over 29. So that's what my y is. And then x from any one of these equations is minus 2/7 y plus 11 over 7. So this is minus 2 over 7 times y, which is minus 89 over 7 plus 11 over 7. So if I'm lucky and my arithmetic is correct, this is something over 49. 2 times 89, it should be 178, plus 11 over 7, which is 77 over 7 over 49, which might be 255 over 49. So if my arithmetic is correct, and I never believe it is, I would get x is equal to 255 over 49, and y is minus 89 over 29. And then if you plug into this equation, these equations, if it's correct, you have a solution. If it's not correct, that just means you made a mistake in arithmetic somewhere. So you go back and you correct it.
I have a question.
Yeah. Go ahead.
Where it says 178 over, I believe that's 49.
Yeah.
How did you get that?
Minus 2/7 times minus 89 over 7. And just multiplying these two fractions. This
Oh.
times this is this. And 11, and I need, then this is denominator of 49. So I want 11 over 7 as a fraction over 49. So I multiply the numerator and denominator by 7. So I get 77 over 49.
Okay, thank you.
All right, well, maybe at this point I will stop because, and then in our next class on Monday, I will describe Gaussian elimination more carefully, where you're not making, you're not necessarily solving equations in the fastest possible way, but you're guaranteed that you will have a solution. So you will have an algorithm, a computer algorithm, if you like, a program, or something which is guaranteed to work if you carry out the steps. And it's all written out legibly and nicely in the text, in the notes. It is section 1.4 on page 31. So it's worth reading that and looking at the examples, and the homework for that will be in 2 weeks, I guess. Right. Oh, okay. Any other questions about everything that is?
I have a question, but it's regarding the homework.
Go ahead, that's fine.
Do you have any resources that we can use to approach the proof problems? Like how do we get the intuition to know like the different steps?
Well, you study the proofs in the text, which are written out pretty carefully, and make sure you understand line by line, sentence by sentence, what the justification for everything is. And I don't know any shortcut other than that. It's just a matter, I mean, well, you have the proofs and the methods that are used in the proofs, and those are the methods that are used in the problem, certainly. And it's just a matter of thinking hard and using a lot of paper and pencil work, going through the proofs carefully, and then trying to see what strategy, what ideas, what methods would allow you to prove whatever you're asked to prove in one of the homework problems. But it's an art, it's a skill, but that's what mathematics is. In mathematics, it's not just calculating things the way you do in calculus, or solving systems of equations the way we're doing here a lot of the time. That's an important part of it. But you have to understand why something is true and be able to prove that it's true.
Okay. So there's no real way to check your proof to verify it's true, right?
Well, there is. It's like checking that your reasoning at every step is correct, and that there's no ambiguity or uncertainty, or you're not making a statement that's not justified.
Okay.
So it's better to err on the side of writing down a lot rather than writing down a little, right? To include as much in the way of the proofs as you can. That's a good thing to do. But that's, that's what you have to learn. And if you're going to be, if it happens that you're majoring in math and you're going to be taking a lot of math classes, then you'll be doing proofs in almost all of your 300 and 400 level classes from now on, as well as computing stuff.
Okay, thank you.
Okay. All right. See you all on Monday. Have a good rest of the week. Bye all.
Oh yeah, one question. When are you going to be doing office hours?
So I usually do them quite a bit, but and I certainly respond to email requests for office hours. Because of this Labor Day weekend and the start of the semester, I've been sort of slow at getting it going. I try to avoid, so starting next week, probably I'll have 2 or 3 or 4 office hours a week. And I'll have several of them in the evenings because I know that people work and have classes during the day. But what is a good time for you in general? You means anyone who's listening.
Either Fridays or the weekend.
Oh, okay. So maybe I'll arrange something for Sunday. I'm traveling on Saturday, but maybe sometime Sunday afternoon, I'll set up one. Yeah. Okay. All right. Be well all. Bye.
Thank you.